Now, in the last section, we were talking about correlation and coefficient of determination, but I would like to delve in a little bit more and try to interpret the residual standard error. Before I do, I'm going to repeat again as far as the data set or the last data set that we're working from. And again, this data set was pulled from Kaggle.com, Heart Attack Analysis Prediction Dataset. And as you can see here, it had a bunch of great attributes that we were able to use to determine the correlation and the coefficient of determination. Now, I want to delve in a little bit more and try to interpret the residual standard error. But before I do, I just want to go ahead and import my modules and load the data set into a data frame called health2. And if you recall, this is what the data set looked like. Now, I want to pay attention to two variables. The first one is this one, which is the maximum heart rate achieved. And the second one that I want to pay particular attention to is the age. Now, if you recall, if I wanted to determine the correlation between those two variables, I would simply type health2, the maximum heart rate variable, and the age. And last but not least, I need to type correlation. All right. Now, as you can see here, again, in statistics, when it comes to the correlation, R, the coefficient R, it measures the strength and direction of the linear relationship between two variables. In this case, thalach and age, which is the maximum heart rate versus the age variable. And right off the bat, we see that there's a strong downhill negative relationship, or actually it's zero point 0.4, so I would say more on the weak to moderate relationship, but it's still downhill because it's negative. Now, if you also recall from the last section, we created a ordinary least squares regression model. So I'm going to go ahead and type the following. And last but not least, I want to print my OLS, ordinary least squares regression results. I can do that by typing the following. Now, what I'm going to try to do is determine my residual standard error. Now, the residual standard error is the square root of the residual mean square. And just to kind of sum it up, it's a measure used to assess how well a linear regression model fits the data. Now, there are a lot of calculations that factor in to determine that value. First thing that one needs to do is determine the residual sum of squares, the SSE. And just to repeat, we've done that before by creating an analysis of variance table. Now, one would need to import the necessary packages, in this case, a statsmodel.api, and then invoke by using the stats_ANOVA_LM function to create that ANOVA table for one or more fitted linear models. So first things first. All right, perfect. Then the second line, to create an analysis of variance table, I would type the following. Now again, the ANOVA is not something new. It's been around for a while and derived initially by a statistician called Ronald Fisher. And I wanted to mention that just due to the fact that I entered type equals 2. And just kind of quick description, when the data is unbalanced, there are different ways to calculate the sum of squares for ANOVA. There's 3 approaches, commonly called type 1, type 2, type 3. sum of squares. And there's definitely tons of literature about this. So the last part, the last line, I want to type print AOV table. Right. So right off the bat, we can see the sum of squares, the residual sum of squares, which is right over here, 133,279. So one way to pull that value from ANOVA, you just invoke results and use the attribute SSR. All right. Now the second part I want to talk about is the residual degrees of freedom. So right over here, you see the number of observations is 303, and the degrees of freedom residuals is 301. Now for a simple linear regression, p equals 2, so which is regression has 2 parameters. So typically the residual degrees of freedom is n minus 2. So in this case, if n is 303 observations, you subtract 2. That's how you get the value of 301 when it comes to the residual degrees of freedom. All right. And as you can see here from the ANOVA table, that's where you see the value of 301. Now to be able to pull that directly from the results from the OLS regression results, one can simply print the residual degrees of freedom turns out to be degrees dot df underscore resid. Right off the bat, you see here's your value of 301. Now the next part that I want to talk about is the residual mean square, which is the sum of squares divided by the residual degrees of freedom. So just kind of to type that for you, it's SSE divided by n minus p. So this is 301, and SSE we figured out the value to be 133,279. So one can simply state results dot and use that attribute again, the regression sum of squares divided by the residual degrees of freedom, that value. It gives you the residual mean square, which is 442.8. Now, this gets us to the finale, is to determine the residual standard error, which is the square root of MSE. So over here, if I type MSE equals MSE, then the residual standard error is just the square root of MSE. Oh, and let's not forget to print it, which is 21.04. And in this case, because I am looking at my maximum heart rate versus age, the value as far as the units here is beats per minute. Now, before I try to explain that further, I want just to show you that there is also an easy way to pull that value, the residual standard error, without having to go through all this over here. Simply, all you have to do is type mp dot square root of results dot scale. This will give you the residual standard error from the ordinary least squares regression results. Just to confirm, I run it and the value is identical. So again, this value over here is the residual standard error, which is 21.043 beats per minute, a little easier to determine. Now one would say, okay, well, is there an acceptable threshold for a residual standard deviation or residual standard error, which is the same? The answer is it really depends and it's based on your experience in the domain, right? So of course, the smaller the residual standard deviation error, the better the model fits the data. And if that value is unacceptably large, then consider using a model other than linear regression. Great. So Investopedia has some key takeaways, and I provide the link over here if you want to read up more on the topic. When it comes to the key takeaways, is the residual standard deviation is the standard deviation of the residual values, or the difference between a set of observed and predicted values. The standard deviation of the residuals calculates how much a data point spread around the regression line. The result is used to measure the error of the regression's line predictability. And of course, as I mentioned earlier, the smaller the residual standard deviations compared to the sample standard deviation, the more predictive or useful the model is. Now, just to visualize this a little bit better, I'm going to go ahead and copy and paste some code to create a scatter plot of the maximum heart rate versus age. And of course, what you see here when it comes to the markers in red, that's your target of more chance of having a heart attack versus less chance of having a heart attack. Now, I created also a regression line. And as you can see here, there is a moderate downhill negative relationship between heart rate versus age. And based off of our residual standard error, one can say that 68% of our data sit around one standard deviation from the average. So in this case, plus minus 20, what did we say? 21 beats per minute or so. So if you see over here, and if you look at a bell curve, about 68% of our data is within that one standard deviation. Now, one can tighten this up a little bit more, but in this case, we're sticking to simple linear regression and wanted just to remind you that in linear regression, the error terms are normally distributed. And because of the fact that they are normally distributed and there's a normal distribution, is that 68% of the data will sit around that one standard deviation from the average. Therefore, 68% of the errors will be plus minus one residual standard deviation. So in this case, our standard deviation, we figured out the value to be 21 beats per minute. So that's what I'm talking about over here. So for our example, our regression equation predicts that our residual standard error will fall within that plus minus 21 beats per minute. So just to repeat, our residual standard error, it's a measure of the precision of a model prediction, which we were able to assess quite nicely. So one can argue that based off of this data set, when it comes to age as a predictor variable, if your maximum heart rate is above, let's say, 160 from age 40 to 50, then there is more of a chance of a heart attack. And as someone ages, that maximum heart rate goes down. But there are outliers, such as the marker in blue. But again, as a predictor and a response variable, as the age increases, that maximum heart rate decreases, as can be seen from that regression line that we have formed, where you have that threshold, where any heart rate above that threshold would be an indicator of having more of a chance of a heart attack, as can be seen on the red markers from the scatter plot. This is excellent. Now, the relationship is moderate, but again, there is a relationship between the two variables. This concludes our section on SLR models, residual standard error.